Hi, my name is Michael Radushkin, and this is Lab 4 Circuits and Capacitors. We'll first start with a brief introduction of key concepts, followed by the experiment, followed by a post-lab discussion. The purpose of this lab is to predict and examine the behavior of circuits with resistors in parallel and series, and the behavior of ohmic resistors and capacitors. The models and physical principles that will be used throughout the lab include Ohm's law, which is the change in potential is equal to the current times the resistance, the capacitance formula, which is the capacitance is equal to the charge divided by the absolute value of the change in potential, the loop rule that in a closed circuit loop, that the summation of the change in potential is equal to zero, the node rule that any current flowing into a node has to equal the current flowing out of the node, and the concept of linearization. And now onto the actual experiment. Within the experiment, we will use two different circuits. The system for these circuits are obviously the circuit itself and also any multimeters that we use to measure different variables. The surrounding for these idealized circuits are none. And the initial conditions for these circuits are that both batteries have 1.5 volts in both circuits. In the first circuit, there is a 47 ohm and 100 ohm resistors in series. In the second circuit, there is a 200 millifarad capacitor and either a 10 ohm or 20 ohm light bulb. So in this first circuit, we were asked to find the current flowing through the circuit. And using Ohm's law, we were able to determine that the current is 0.02 amps. And doing the actual experiment, we found the exact same result, whether the ammeters were inserted regularly or backwards. When we replaced the top ammeter with a voltmeter, the voltmeter showed us a reading of 3 volts because from the battery, we saw a potential of 3 volts, but on the other side, near the resistor, there was 0 volts because this circuit, though it is a closed circuit, does not have current flowing through it because the voltmeter theoretically has an infinite amount of resistance, thus not allowing current to flow through it. And the ammeter proves this point as it showed 0 amps flowing through the bottom half of the circuit near the resistors because the voltmeter has provided us an infinite amount of resistance and thus no current flows throughout the circuit. So now we were asked to basically prove the loop rule that the summation of potential is equal to zero. And when we put the voltmeter up to these different points, we were able to find the potential difference at these different component sections. And when we summed all of them together, we in fact showed that the summation is equal to 0 volts. So for the final section of this first circuit, we were asked to look at the voltmeter in parallel versus the ammeter in parallel. And because the voltmeter has a theoretical infinite resistance, none of the electrons want to actually flow through the voltmeter, and thus the current basically was left uninterrupted and was left at 0.02 amps. The ammeter, on the other hand, theoretically has 0 resistance, and thus a large chunk of the electrons would want to throw through the section of least resistance, and thus it created an overall greater current of 0.06 amps. Finally, we were asked to use Ohm's law to show the resistance at the resistors and the wire and ammeter. And we roughly were able to get similar results that the 47 ohm resistor is equal to roughly 48 ohms, and that the 100 ohm resistor is roughly equal to 102 ohms. And we also showed that the wire and ammeter both give 0 resistance. Now, looking at the second circuit, we were asked to observe the behavior of the light bulb. And in both charging and discharging, the bulb started out bright, but then it quickly dimmed. But in the charging capacitor, the current starts off as normal like it did in the first circuit, but eventually it slows down to 0 when the capacitor is fully charged. But with the discharging capacitor, the electrons go in the opposite direction, but eventually also slow down to 0 when the capacitor is fully discharged. And both of them exponentially decrease. And the timing of that charge and discharge are shown in the slide. And finally, in the second circuit, we were asked to determine the voltage at different times from 0 to 20 seconds. And then we use the concept of linearization to determine the RC value, which is the resistance times capacitance. And so when we use the linearization property, we took the slope, which we found was negative 0.164, and then we're able to solve for the RC, which was 6.098 seconds, which from theoretical calculations is very close to the theoretical calculation of 6 seconds. And now some post-lab questions. The only possible error in this lab is not stopping the simulator time at the same time as the timer. If we were using a real ammeter, there would be a small amount of resistance, so the reading on the ammeter in a circuit would actually be less than the idealized ammeter that has zero resistance. And if we were using a real capacitor, real batteries, and real wires, the batteries, capacitors, wires would have some resistance. Thus, the capacitor would not fully charge instantaneously, while ideally, when there's no resistance in the batteries, wires, or capacitors there, the capacitor would charge up instantly.